Swayam Prabha. Digital India. Educated India.
Welcome back to mechanics and control of robotic manipulator. So last class we have seen that so what is individual rotation matrices, and then we have given an introduction to what you call compound rotations. Even in that class itself I told that we can actually like do two things. If you are actually like rotating any frame with respect to, you can say, fixed axis, then you have to actually like you can say pre-multiply that rotation matrix, whereas if you are rotating with respect to, you can say, moving axis, so then you have to post multiply. So that we have seen, and then we have seen that there are several common representations are available. In that, two of them we are going to see in this particular lecture. So one is actually like we call Cardan angle, the other one is we call Winkel or Bryant angle. So simply we call one is actually like a global fixed, so the other one is Euler angle. So let us actually like move to that into the lecture. So what we are actually like going to see is actually like one is what you call global XYZ fixed angle, which we simply call RPY in the sense roll pitch yaw, or some people call it's a, you can say, Winkel angles. So whereas the other one is actually like ZYX Euler angles, or simply we can call Cardan or Bryant angle. So let us actually like move one by one. Okay. So for understanding that, we have taken two frames. So where A is the fixed frame, okay, and B is the final body frame. So now you can see that these two are actually like having different representation. So at least we can see like three orientational information is required. Straightforward you cannot get simple with one or two rotation. So in that sense, what we can actually like try to do, we'll start rotating with respect to x axis, so certain angle, then we'll go to y axis, certain angle, then z axis, certain angle. So here I make it inconveniently, it is actually like make 90 degree each. So for example, if I take xa axis, rotate the frame, so then I will get a new frame, that would be I call rotated with respect to fixed xa axis. So then I will get one rotation matrix. Then I will take that corresponding frame, again I will rotate with respect to ya frame, then I will get another frame. So finally I will rotate that with respect to za, which is fixed frame, then that will finally end up with the B matrix. This is what we are trying to do. So in that sense, we will see first what we are trying to do. We are trying to rotate a gamma angle with respect to, you call, xa cap. Okay. So now what it will do, it will actually like take this here and this goes here. So I will get a new coordinate. Okay. So that I am calling as a B1. So what I did, so this would be actually like xa cap I taken as the reference, I rotated. So now I got a new frame, that would be x1, so y1 and z1. So this is actually like one new coordinate. So now what I am trying to do, the second one, I take ya cap as the common and rotate this again with some other angle called beta. Okay. So now I am actually like first rotated. So rotation matrix of 1, in the sense the B1 with respect to A is actually like rotated about x axis and a gamma angle. So now we will go to the next one. So I am rotating this with respect to the fixed axis, so ya. So I am rotating in a beta angle, so this is the rotation angle. Okay. So this much angle I taken. So now I will get new thing. For simplicity I have taken beta as 90. So what I will get a new frame called B2, right. So now you can see like what I will get Ry beta, which is actually like in right rotation matrix of B2 with respect to B1, right. So this is the second one. So that is what we did. So now finally what we are trying to take, we are taking the za cap, okay, and rotate you can say alpha angle and trying to see what would be the frame representation. So now if that is the case, what we can see, so I take this and rotate alpha angle, this is the positive rotation, right. So I take this, for convenient I take 90 degree, what I will get, I will get this, right. you can see. So now what I did z axis rotation of alpha, where that will give, so B to, so B, right. So this is what I get. So now what actually like we did, so we did that one simple example, say that if you rotate everything with respect to fixed axis, then you have to pre-multiply. Then what your actually like final rotation matrix supposed to be, so your rotation matrix R, you can say B with respect to A should be, so first you have rotated, you can say like x axis as a gamma angle, which actually like give rotation matrix of B1 with respect to A. Then you are actually like taken the second one, then you pre-multiply. So then you will get R y beta. So this will give 2 to 1, B to 2, B1. Then final you rotated about Z as alpha. So that would be given actually like what you can say. So B2 you call B2, right. So this is what you get it. So that is what we are also writing, right. So now if you see that this is the final rotation matrix of B with respect to A. So I hope this is clear to you. Now we will put the individual rotation matrix. If it is x axis rotation, so you know what, if it is y axis rotation, what would be the individual matrix, if it is z axis rotation, what would be the individual matrix. Now you are clear why we have attempted this in the previous lecture. So now we will substitute those values directly. So this is the x axis rotation, and this is the y axis rotation, and this is the z axis rotation. You multiply this end, so you will get this bigger matrix, right. So this bigger matrix is what? So this is what the rotation matrix of B with respect to A, right. So now if you are actually like taking this into the consideration, so what would be this equivalent? So this is the bigger matrix. So I have taken the same matrix, but I have taken a conveniently safer place where you can see. So now this is equivalent to what I am writing as R11 to R33. So now what this is equivalent to R, you can say alpha, beta, gamma, where alpha is actually like rotation about z axis. So beta is actually like rotation about y axis. This gamma is actually like rotation about x axis. So I want to find out what is alpha, what is beta, and what is gamma if I know this value. Okay, if I know this final end as this, can I find this? Okay, so for that what we are trying to do, we are trying to use this relation. So if I take these two, okay, so for example if I take R33 and R32, for example R32 divided by R33, what that will give? That will give tan gamma, right. So similarly I take these two, so what that will give? So that will give something like, so I say like R21 divided by R11, so that will give tan alpha, right. So like that I will get 1 by 1, right. So once I get this, so then I can actually like use it for this, and I can actually like use by substituting this, I can find the beta as well. So that is what I am writing as a equation. So you can see like if I actually like if I actually like square and add and take the square root, what I will get? That would be get it equivalent to cos beta, right. So that is what you get as a cos beta, right. So then what this is actually like will give, you can say sin beta equal. So then that is actually going to give, so beta. So you can actually like look at it. So R31, so previous, so R31, so this is R31 which is minus sin beta. So R11 and R21, so if I square, what happened? So cos alpha, okay, so squared, so cos beta squared plus, so sin alpha squared and cos beta squared. If I take the square root, what it will give? That will give cos beta. So then you can actually like find, so the beta by taking this tan beta, how I can write? So tan beta I can write in the way, right. So sin beta divided by cos beta. So here sin beta is actually like a minus R31. So this we taken as, so R11 squared plus R21 squared square root, right. So this is what we have taken as tan beta, that is what we have used. And here we are using a 2 argument tan. What that mean? So you know the tan will give a quadrant basis. If I take, you can say x positive, y also positive. So what angle, for example, this is the location. So what angle will give? This is the theta, right. So now you assume that x is negative and y also negative. So then what if you substitute with a single argument? So tan inverse of, so minus y divided by minus x. So it becomes, so tan inverse of y by x, right. So then it says that although that is there somewhere here, okay, it's a third quadrant, but it shows that it is in the first quadrant. So that's why we are taking a tan 2 argument, in the sense it is actually like quadrant dependent. So based on the, you can say the sign of x and y, it differ. Similarly, if you take this, okay, so in the sense y is negative, sorry, y is positive and x is negative. So what it's supposed to give? So tan inverse of, so y minus x, but this is equivalent to tan inverse of, so minus y by x. Then it will give this value, right, rather than this angle. So in the sense you have to actually like take each quadrant and do it. That's why we are using the arc tan 2 argument, okay. So then you are clear that it is quadrant dependent. So similarly we will actually like do the what you call the other angle. So you can see like alpha can be obtained again with respect to the same thing. So you can take these two. So where that would be equivalent to what? It is equivalent to tan, you can say alpha. So you can see like a sine alpha divided by cos alpha. So in this case what it will come? It will come like r, so 2 1 divided by r 1 1, right. So that we can actually like use it, but the cos beta would come, so we put divide by cos beta, okay. So that is what we are actually like using it. So now you can see that this will give alpha. The similar way you can actually like take these two equation and substitute once you know the cos beta. So then you can take r, you can say 3 2 divided by r 3 1 whole divided by cos beta, okay, sorry 3 3. So then that would be equivalent to tan, you can say gamma, okay. So then you can actually like find it, right. So this is the way we can find for the global xyz, which we call, you can say Winkle angle, we can actually like find it, okay. So let us go to the next one, which is we call the same thing, but we are writing in a moving frame, which we call Cardan or Bryant angle, where we have taken this and we are actually like trying to find. So in this case what first? So first z axis rotation, so then y axis rotation, finally will come with x axis rotation. So but what with respect to the moving frame, okay. So in the sense right now we assume this is the moving frame, so I rotate about this, okay, I call probably a psi angle. So then what it is coming as a new coordinate frame, from that I will take y, I rotate, then that will give a new coordinate frame, from there I will rotate again x, then finally I will end up with this, okay. So we will see that. So first I rotate psi angle here, so I will actually like get a new matrix, sorry, new coordinate frame, this become 90 I taken, so this become xa become, you can say here, and ya become here. So that will give a new coordinate frame, which I call B1. So now what the second stage? Second stage I have to rotate with respect to this. So before that what we did? We did this, right. So we will go the next one. So next one I am rotating about y1 theta degree, theta angle. So now what happened? This would actually like go here and this come here for 90 degree rotation. So you will get a new coordinate frame, right. So now what we did? We did actually like ry, so theta angle, so which will give 2 1, right. So now again we are rotating with respect to this. So we are rotating again some other angle called phi, so that will get here. So what you can actually like rotate this 90 degree, you will get it, right. So that is what we are actually like doing it. So phi angle, and positive rotation all about, you can see based on the right angle, right hand. So your rotation axis you keep it your thumb finger, and where these 4 fingers are coming, that is the positive rotation. In this case this is the thumb finger, where it is coming outward is the positive rotation, in the sense y2 become, you can say, parallel to z, and z2 become parallel to y but opposite direction. That is what here, right. So now we got the new coordinate which is equal to your original intended, right. But what angle we did? So x with the phi angle, so this gives actually like b2 2, right. But what we did here, actually like we did everything with respect to moving axis. So then what we have to do? So first we did 1 to a with z psi. So the second one is actually like y, that is supposed to multiply. So in the sense r y theta, which gives this. Then finally you did x, right. So which will give b2 2. So this is what you can say like z y x Euler angle, which we simply call Cardan or Bryant angle. Okay. So now you can see like what you obtained. This is what the final matrix. Okay. So now this matrix, again you can substitute the individual rotation matrices and you multiply this. So what you will get, this bigger matrix. So this bigger matrix again we can actually like equate to this, right. So then what you can find? You can find the psi, theta and phi, what we did in the earlier case. The same way we can try to find. So what that? So you can see like the same way we have done, and this is theta is actually like a pitch angle, okay, local pitch. So this is a local roll and this is local, you can say, yeah. So in the other way around you can actually like say that this is actually like heading angle, this is actually like bank, and this is the attitude, right. So these all we have obtained. So now there would be one bigger questions will come, one bigger question will come. What that? So sir, you have used the compound rotation and that to two different representation. So but what is the relevance into this course? So there is a relevance because we are trying to find out one frame to another frame with respect to, you can say the orientational information, what you call rotation matrix. This rotation matrix would be consist either alpha, beta, gamma, or it would be in the form of, you can say like phi, theta and psi. So either way you have to write, but is it very simple? No. If it is actually like rigid body, that too like only one body or maximum you are using two body system, you can easily do this. However, if you are using multi-body system, for example, you have a manipulator which is having a several body. So one body to another body information would be having, you can say, 3 translational information and 3 orientational information. The translational information is very straightforward because it is actually like given as a position vector. However, the orientational information is not straightforward. You cannot directly write alpha, beta, gamma. So you have to actually like get some rotational matrix. So for finding rotational matrix, how will you get this alpha, beta, gamma? So this is one of the question, and there is no straightforward technique to use this. So that's why people are actually like bringing some other, you call, convention. So especially for, you can say, manipulator, either it is actually like serial manipulator or parallel manipulator, the general representation may not be explicitly used because the constraint is actually like it is composite. The composite is giving some complexity. Okay, this complexity is actually like arises. So there is a huge question. So in addition to that, if you have n bodies, so how many informations you should have? So one body to another body information you should have 6 valuable variables, right? This is 3 translational and 3 orientation. If you have n bodies, how many variables required to describe the entire system in a, you can say, kinematic form? You should have 6n variables, right? Although the total variable to describe the overall system, although in spatial it would be having only 6, which is we call degree of freedom, but the individual, you can say, representation of one body to another body required 6. If you have n bodies, you have 6 into n. So can we reduce it, or can we use some simplification, or the rotation matrix can be modified as some kind of simplified form? So there are certain forms which we people use in robotic community. So one is actually like one of the popular method called Danavitt-Altenburg. So the other popular method is actually like screw algebra. So unfortunately this particular course we would not be talking about screw algebra anymore. So here we would be talking about Danavitt-Altenburg. So in the next lecture we would be talking about that. So how to represent, how the parameters are actually like simplified or reduced, or how we are actually like simplify the rotation matrix, all you would be seeing. So until then, see you. So I hope you are actually like clear about what is Winkel angle and what is Cardan and Bryant angle. In general, you would know like what are the representation. So the Euler would be moving frame representation, and the other one is global fixed you can say x, y, z, which is actually like most of the manipulator community people uses, and the mobile robot community or rigid body dynamic people uses actually like the Euler angle, especially z, y, x, okay. And very few you can say aerial robot or spatial robot community people use is that y, z, or you can say z, y, z convention, okay. So with that I am closing. Even some other convention also there, but that and all will come into the upcoming lectures. So with that I am actually like saying thank you, see you then, bye.